Hi, I want to talk to you about the questions on the torque WebAssign. We're just going to quickly talk through them. Some of it we haven't talked about yet, but a lot of it you can do. So for this first one, distinguish between a rotation and a revolution. I was just going to give you the answer anyway. A rotation is when the whole body is rotating around an axis. Think about the Earth going around its axis every day. A revolution is when a body goes around an axis that's outside itself. Think about the Earth going around the sun once a year. So that's that distinction. For this one, it's a little confusing how it's set up unless you realize that the net torque is zero. So the idea here is these two people are balancing out. They're creating a zero net torque. And then the other answers come from just the fact that you know that torque equals R cross F. So, and you know they have to cancel out. Instead of using positive and negative, this uses clockwise and counterclockwise. So that's very straightforward. Torque equals I alpha, alpha is 0. For this one, you're thinking again, torque equals R cross F. You want to maximize torque by either maximizing the distance from the fulcrum or the force. This is very straightforward. Again, torque equals R cross F. You know the force, you know the R vector. The first situation has a theta of 90 degrees, second has a theta of 60 degrees. I'm just remembering that R cross F is R times F times sine of the angle that separates them, because you want the perpendicular part. We did a problem a lot like number 5 in class. Using the right-hand rule, we can see that not all of these forces are working as a team. Some are positive and some are negative. So remember, clockwise torques are negative, counterclockwise are positive. So when you're setting up your net torque equation, you're going to want to keep that in mind. These are like F equals ma questions. You start with net torque equals I alpha, that's always true, and then your second equation comes from the picture. So how I would set up number 5 here is with net torque equals I alpha, that's my first equation. My second equation is net torque equals torque A plus torque C minus torque B. Or, yeah, that works. Whatever. You have to combine the two that are working together and then subtract the one that's working against them. Same idea here. Keep in mind that if here's the R vector for F4, here's F4, the angle between them is 0 degrees, and so F4 does not create a torque, but the other three all do create torques, and they're all 90 degrees. Okay, so here we start getting into some good stuff. We do have a acceleration here. What's interesting is it asks for both accelerations of particle 1 and particle 2 in meters per second squared. So we're looking for the tangential accelerations of these two particles. I'm 99% sure. Now the thing that they share in common is alpha. Since they are attached to the same object and share a fulcrum, they'll have the same angular acceleration. And so you can start with torque equals I alpha. This is kind of like the seesaw problem where you have the two weight forces acting to try to make the rod spin different ways. And so then you want to figure out alpha, and then remember that tangential acceleration equals r times alpha to get the answers. 8 is kind of like the problem we did in class that was on the back of the handout that had the blocks sliding down the incline and making the pulley spin. So this is a systems problem where you have F equals ma for block 1, F equals ma for block 2, and net torque equals I alpha for the pulley. Number 8 I want to go over in class tomorrow, but definitely you can set it up and get started on it. Okay, so this one has torque, it has F as a function of t, and the inertia is constant. Torque equals the integral, let me go over this one with you. I have to double check. I feel like torque equals the integral of FDR, don't worry about 9. I'll figure it out. This one's not so bad. Hey, we did this one in class. 10 we did. You know R, you know the torque, you know alpha. And so you're looking for I, and then you're looking for M. We did this one together. 11 we will do in class. It has a cross product with vector components. We're going to use a matrix to do that. So we'll review number 11 in class. And 12, again, is a lot like the ones we've done previously, where we have some torques working as a team, some working against, and you have to do, oh, and you're not even looking for alpha, you're just looking for the total torque. So you're just going to add them up. So now you have all the tools you need to make an honest attempt at most of this WebAssign before I see you tomorrow. The only ones that the only one that I haven't shown you how to do yet is number 11 and number 9 with the calculus and the cross product. And again, number 8 is a little bit labor intensive, but you certainly can set it up. See you tomorrow.